Good day, everyone. Welcome to our class. Today we're solving circuit questions, so questions involving circuit diagrams as far as electricity or electrical energy is concerned. Now, before we move on, I'd like us to take note of two things that confuse most of us sometimes when we're solving circuit questions. We have what we call electromotive force, which is also our EMF, and then the potential difference, which is also our voltage. Now, let's define both of them. And then after that, I'm going to use a nice circuit diagram here, a very simple one, to differentiate or to explain both of them. Okay. Now, the electromotive force, we're saying that is the force or electrical pressure that causes a current or charge to flow in a circuit, equivalent to the potential difference between the terminals, and it is commonly measured in volts. Or we can say that it is the energy provided by a cell or battery per coulomb of charge passing through it. Good. Then the potential difference of voltage, which is also measured in volts, we can say or we can define it as the work done per unit positive charge in moving the charge from a point of lower potential to a point of higher potential through a load. Now, a quick circuit diagram here. But before that, let me just draw another circuit diagram to explain electromotive force and then the potential difference. Good. Now, if I have this as my cell, now this is my positive and this is my negative. Let me just connect it to a key here and then connect it to a load here. Let's say a bulb. Good. Now, once the key is closed, if I close my key, it means that we are expecting electrons to move in this direction and then currents to move in this direction, since current and electrons are moving or move in opposite directions. Okay, good. Now, the only way you can have currents moving is when these positive charges and these negative charges flow in the connecting wires. Okay, so that force that pushes the electrons and then the positive charges to move out of the cell is what we call the electromotive force. Okay, so that force is what we call the electromotive force. And once you have current and electrons moving through the cell, then we can be able to measure the potential difference that has come out. Now, remember, not all the protons or the positive charges and the negative charges will be able to move through the cell. Okay, so assuming the whole cell is supposed to provide 12 volts of potential difference, or yes, it's supposed to provide 12 volts, because the cell itself has internal resistance. So that is how come you need the force to push it out. So there is an internal resistance in this cell that is preventing all the positive charges and then the negative charges from coming out. And because of that, you are not going to get exactly 12 volts, and you are going to get less amount, so that you can be able to measure the potential difference. So the potential difference itself is that number of protons and electrons that have been able to leave the cell and are moving through the system. Okay, so if this is our bulb, which is representing our load, then we can measure the potential difference across the bulb to indicate the amount of charges or electrons and protons that are moving in the cell. Okay, so that is the little difference, or that is the main difference between the potential difference and then the EMF. So if I come back to this diagram, you will see that the potential difference is always measured across the load. This is our load, which is the resistor, and we can measure the potential difference across the load over here. Now, the EMF is also always here, and immediately you hear EMF, then the one thing that you should know is that once you have EMF here and you have cells trying to move out to provide current and then electrons in this direction, there is going to be an internal resistance. So the internal resistance is the resistance of a cell, or is the resistance that every cell has, that is preventing the electrons or the positive charges and the negative charges from leaving the cell so as to provide current to the whole system. Okay, and we represent it with small r. Okay, so in a cell like this, there is an internal resistance small r, and then there is the resistance of the cell big R. Okay, so according to Ohm's law, We know that V is equal to IR, but immediately internal resistance comes into play. Then we are going to have an equation E to be equal to I multiplying into bracket R plus small r. So this is what we are getting as soon as we have EMF coming into the system. Now let me just open up the equation and explain a few things over here. Good. Now I have E to be equal to I into bracket R plus R over here. Good. Now if I expand this, I'm going to get E to be equal to IR plus I small r, so that E becomes equal to V plus I small r. Now looking at this expression, you realize that we have our EMF here, which is representing E, and then we have our potential difference here in this equation, whereas this represents the current multiplying the resistance out. Now back to the circuit again. You realize that the resistance here, or the internal resistance here, is preventing all the charges from moving out of the cell. And because of the work that it is doing, there is what we call lost voltage in the cell. So every cell will have a lost voltage due to the internal resistance of the cell. And that lost voltage in this equation is what we have as big R small r. So big R small r here is representing the lost voltage. So that when you add the lost voltage to the voltage in the cell, then you are going to get the EMF. Okay, good. And this IR here, which is also representing our V, is what we call the terminal voltage. Okay, the reason why we call it terminal voltage is because it is the voltage that is currently working as far as the load and the circuit is concerned. Okay, so this is the terminal voltage and this is the lost voltage. And in most cases, when you see cells, you realize that as you're using cells, they become very hot. They become hot. So the lost voltage is dissipated, or is leaving the system in the form of heat. Okay, so from this equation, we have our EMF, we have our voltage V, which is also known as the terminal voltage, and then we have our lost voltage. The lost voltage is IR, and it is coming as a result of the internal resistance of the cell that we have here. Thank you. Then let us try and see if we can plot a graph from this equation, E to be equal to V plus IR. If I make V the subject, then V is going to be equal to E minus IR over here. Or better still, I can say that V is equal to minus IR plus what? E. Good. Now, I want to compare this equation to y is equal to mx plus c. Now, this is a mathematical equation that we are mostly using when you plot a graph. Okay, so this is our y-axis, this is representing our slope, this is our x-axis, and this is our intercept. Good. Now, let's quickly see what happens when you plot a graph. So, if you plot a graph here, and in the graph, I have my voltage, which is in volts, and I'm plotting it against my current, which is in ampere. Okay, and I draw a graph here. You realize that from the graph here, this represents the slope. So the slope of the graph is going to be at this side. Okay, now look at this graph very well. You realize that from the graph, the slope is going to be m. Okay, so the slope is negative r. In comparing this equation to this equation, the slope is going to be negative r, and the EMF is the intercept. Okay, the intercept of the graph, and it's mostly on the y-axis. Okay, so anytime you have a graph of V against I, and from this equation or from this relation, you have to compare the graph to y is equal to mx plus c, so that the EMF becomes equal to the intercept, and then the slope becomes equal to negative of r, since you have plotted I against vein, and then this is what we get. Okay, let us try and solve a few questions. But before that, let me just explain another thing. We have E again to be equal to V plus IR. Now, mind you, the only time that we have internal resistance in a cell is when a circuit is closed. Okay, so when you have a circuit closed, you can have current flowing through the circuit, and therefore you can make sure, or you can attest to the fact that you are going to have internal resistance in the cell. However, when the circuit is not open, or when the circuit is not closed and you have an open circuit, you realize that there won't be any current in the circuit. Therefore, I is going to be equal to 0. This is when the circuit is open, and it implies that E becomes equal to V plus 0, so that E becomes equal to V. So when you have an open circuit, then you're going to have E being equal to V. This is what happens. Let's move on to solve one question and see. Okay, so we have our question on the board. The question reads, the potential difference across the terminal of a cell is 3.0 volts when it is not connected to a circuit and no current is flowing. Okay, so in our solution, we can say that once we have this, it is not connected to a circuit, so we have 3.0 volts. So that is E to be equal to 3.0 volts. Now, when it is not connected to a circuit and no current is flowing. Now, when the cell is connected to a circuit and current is flowing, so once it is connected to a circuit, then it's going to have an internal resistance which we do not know. So let us connect the cell to a circuit. This is our resistor R. Let us give it a key, but the key is a closed key anyway. Good. So, and we have a current I, which is equal to 0.37 ampere flowing through the system. We're saying that when this happens, the potential difference falls to 2.8 volts. Good. So from here, I have V, which is going to be equal to 2.8 volts. That is my potential difference. The question is asking us to calculate the internal resistance of the cell. Good. Now we know that E is equal to I into bracket R plus R. Therefore, E is equal to IR plus IR. E is equal to V plus IR. So E minus V is equal to IR. So our internal resistance R is E minus V all over I. So this is equal to 3.0 minus 2.8 all over the current, which is 0.37. This is going to give you 0.2 all over 0.37. I think this should give you something like 0.54. So you get internal resistance out to 0.54 ohms. This is very simple. So all you need to know is to remember how to draw a circuit diagram, be able to bring out the equation from the circuit diagram and fix in your values or do substitution, and then you are there. In my next video, we are going to solve a lot of questions as far as the circuit is concerned so that we can follow up and be more interested. Kindly subscribe, sign up to our circuit, and don't miss a thing. Goodbye, good day, we'll meet again. Thank you.